So whenever the 1 mole of any compound dissolve in the water or any other solvent, and in case of water, to give the aqueous solution, the energy involved in this process is called the heat of the solution. Now if I take the example of the NaCl solid, when it dissolve in the water to give the aqueous solution, whatever the energy supplied is called the heat of the solution. This heat of solution is the addition of the two energy. In the first process, what we have to do, NaCl is the ionic compound. It has a very strong lattice. First we have to provide the lattice energy to break the lattice of the ionic compound NaCl. So in the first step, NaCl solid provided with the lattice energy to give the Na positive aqueous and Cl minus aqueous. So again in this process, first we have to provide the lattice energy. As I told you, in the starting of the process we have to provide the energy. In the next step, energy release. In the next step, what happens? Na positive gaseous and Cl minus gaseous, they are surrounded by the water molecule, and whenever they are surrounded by the water molecule, the energy release is called the hydration energy. So in the first step we have to break the lattice by the providing the lattice energy, and in the second step, energy release due to the hydration. So in this process, hydration energy release. Then heat of the solution is the addition of the lattice energy and hydration energy. If hydration energy is more negative and lattice energy is the less positive, heat of the solution become the negative and ionic compound will be soluble in the water. And if lattice energy is more positive and hydration energy is the less negative, then in such case what happens? Heat of the solution become positive. More positive lattice energy, less negative hydration energy, heat of the solution become the positive. And whenever the heat of solution is positive, we can say ionic compound remains insoluble in the water. The energy released by the hydration is not able to compensate the lattice energy. When hydration energy is more, we can say energy released by the hydration is sufficient to compensate the lattice energy. So under such case, heat of the solution become the negative and ionic compound will be the soluble in the water. Then very important, heat of the neutralization. Many student has the doubt in this part. They always ask the different type of question regarding the heat of the neutralization. You need to remember whatever I will explain you now. You need to remember, you need to listen everything very carefully. What is the heat of neutralization? Whenever the 1 mole of the H positive react with the 1 mole of the OH minus, they always give the 1 mole of the H2O. Energy release in this process called the heat of the neutralization. Whenever the 1 mole of the H positive react with the 1 mole of the OH minus, the energy release is called heat of neutralization. And heat of neutralization, whenever the 1 mole of H positive and whenever the 1 mole of OH minus react together, they always release the energy which is equal to minus 13.7 kilocalorie. 13.7 kilocalorie. Now you check this reaction. HCl is the stronger acid. 1 mole of the HCl provide the 1 mole of the H positive. NaOH is also the strong base. 1 mole of the NaOH provide the 1 mole of the OH minus. So 1 mole of the H positive here, 1 mole of the OH minus is here. They react together to give the 1 mole of the H2O. Energy release is again 13.7. But Now you check the next equation. In this one, H2SO4 react with the calcium hydroxide. H2SO4 is also a stronger acid, CaOH whole twice, also stronger base. 1 mole of the H2SO4 provide the 2H positive and 1 mole of the CaOH whole twice provide the 2 mole of the OH minus. So in this process, 1 mole or 2 mole of H positive react with the 2 mole of OH minus, they provide the 2 mole of the H2O. When 1 mole of H positive and 1 mole of the OH minus react, they give the energy 13.6. Then if 2 mole of the H positive react with the 2 mole of the OH minus, they give the energy twice of 13.7. But heat of neutralization, this is the heat of reaction. Heat of neutralization always defined for the 1 mole of the H positive react with the 1 mole of the OH minus. Then whatever the energy release is called the heat of neutralization. This 13.6 represent the heat of neutralization also and heat of reaction also. But this 13.7 is not the heat of neutralization. Heat of neutralization 1 mole of H positive, 1 mole of OH minus. But here you have the 2 mole of the H positive and 2 mole of the OH minus. So this is called the heat of reaction, not the heat of neutralization. If you divide, it is the energy by the 2 H positive, 2 OH minus. If you divide by the 2 cancel out, and heat of neutralization again comes as a 13.7. Suppose if we have the next example, this time I take the acetic acid. It is not the stronger acid. Degree of dissociation is not 100%. NaOH is the stronger base. 1 mole of the NaOH provide the 1 mole of the NaOH provide the 1 mole of the OH minus. But 1 mole of the acetic acid cannot provide the 1 mole of the H positive. So this time OH minus is 1 mole and concentration of H positive always less than the 1 mole. If 1 mole react, 1 mole H positive, 1 mole OH minus react, they release the energy 13.6. But since the H positive is less, they cannot release the energy 13.6. They always release the energy which is less than 13.6. This time energy release minus 13.4, which is less than the 13.7. Now in the next example, HCl is the stronger acid. 1 mole of the HCl provide the 1 mole of the H positive. But sodium ammonium hydroxide, NH4OH, is the weak base. It cannot provide the 1 mole of the OH minus. So HCl provide the 1 mole of the H positive, but this NH4OH provide the 1 mole of the OH minus, which is less than the 1 mole of H, 1 mole. Then what happens if 1 H positive, 1 OH minus react, energy 13.6. But since the OH minus is less, then what happens? This become the limiting region, this become the access region, and energy release is always less than the 13.7. This time they release the energy minus 12.3. Suppose if acid is also weak and base is also weak, one is stronger acid provide the 1 H positive, one is stronger base provide the 1 OH minus, but weak acid cannot provide the 1 mole of the H positive, weak base cannot provide the 1 mole of the OH minus. So they always react together, then they release less than the energy 13.7. This time they release the energy minus 11.9 only. In this means, by this concept we can also calculate the degree of dissociation of the weak acid and weak base. How? What is alpha? Alpha is the degree of dissociation. What is that? What is the energy release and what is the actual heat of neutralization. Suppose if I want to calculate the heat degree of dissociation of the NH4OH, I told you HCl 100% dissociated. So alpha is the, what is the energy release? 13.12.3, and what is the heat of neutralization? 13.7. Then answer will come 0.89, or it is the 89% dissociated. Okay, means 12.3 energy they have released by themselves to whenever they undergoes the neutralization reaction. Okay, so what is the alpha? You can calculate the alpha here also. If I want to calculate the degree of dissociation of the acetic acid, what is that? 13.4. What is the actual energy release divided by heat of neutralization? 13.7. This will provide you the degree of dissociation multiplied by the 100. You will get the how much percentage dissociation is. Look, how much energy released by themselves? 13.4. Then what is the extra energy we have to supply it so that the weak electrolyte can also undergoes the 100% dissociation? That is called the energy required by the energy required for the dissociation. It has the formula energy release minus energy of the neutralization or heat of the neutralization. Suppose if I want to calculate the energy required for the dissociation for this example, then you check what is the energy release. Energy release is the 13.4. And what is the heat of neutralization? Heat of neutralization is minus 13.7. Energy release minus 13.4 minus of minus 13.7. Then how much energy we have to supply? We have to supply energy 0.3 kilocalorie to dissociate CH3COOH 100%. Then next we have the heat of hydrogenation. Whenever the 1 mole of the hydrogen is added to any compound, the energy release is called the heat of the hydrogenation. If I have the unsaturated compound, suppose we have the ethene. In the ethene we are adding the 1 mole of the hydrogen, then what they give? They give the ethane. So what happens during this reaction? This pi bond breaks and sigma bonds are formed. Energy required to break the big pi bond is less. Energy released by the formation of the 2 stronger sigma bond is more. Then less energy supplied, more energy release, reaction become the exothermic. So whatever the energy release here is called the heat of the hydrogenation. Now you check the next example. This is the cis alkene unstable. This is the trans alkene stable. Cis alkene on the hydrogenation provide the energy x1. Trans alkene, which is more stable, on the hydrogenation provide the energy x2. Then you need to remember that always the unstable alkene provide the more heat of the neutralized hydrogenation as compared to the more stable alkene. Unstable alkene cis provide the more heat of hydrogenation. More stable alkene trans provide the less heat of hydrogenation. By the knowing their heat of hydrogenation, we can calculate their stability. The alkene which provide the more heat of hydrogenation is more unstable, less stable. The alkene which provide the less heat of hydrogenation is the more stable. So we can write higher the heat of hydrogenation, less is the stability, means stability of the alkene always inversely proportional to the heat of hydrogenation. Then next we have heat of polymerization. It is very simple. Suppose we have this reaction, we have the formation of the polythene. Then in this reaction, if you see, then 1 pi bond breaks and 2 sigma bond are formed. But for the 1 molecule of the CH2CH2, we take always 1 sigma bond, because 1 sigma bond is the part of the another carbon and only 1 sigma bond is considered under the part of this compound. So what happened in this case? In the first step we are breaking the CC sigma bond, CC pi bond, and in the next step we have formed the CC sigma bond. Then we have to apply this formula, summation of bond energy of the reactant minus summation of the bond energy of the product. Reactant, in the reactant we are breaking bond as pi bond, then what we have, pi bond energy of the CC pi bond minus bond energy of the CC sigma bond. By solving this one we can calculate the heat of the polymerization. Next we have the example bomb calorimeter. This is very important. Many students have the doubt in the bomb calorimeter. They always ask how to solve the question, how to solve the question. Then you need to remember bomb calorimeter is always used to calculate the calorific value of the fuel. What is the calorific value? The energy released by the combustion of the 1 gram of the fuel or any substance. The energy released by the combustion of the 1 gram of the fuel or 1 gram of any substance is called the calorific value. Higher the calorific value, better is the fuel. If any question is given regarding the calorific value, what you have to do? Energy released by the 1 mole divided by molar mass. Just find out the value which provide the higher value, that will be the better fuel. What we do in the bomb calorimeter? In the bomb calorimeter we have a vessel made by the stainless steel. In that vessel we have another small container that is called the bomb. What we do? In this bomb we have a very small crucible, a very small bowl. In that bowl what we do? We take the 1 gram of the fuel and we add the excess of oxygen into it. What I said? We take the bomb. Bomb is also a small vessel which is placed in the big vessel. In this bomb, first we take the 1 gram of the fuel in the small crucible and then we add the oxygen, excess amount of the oxygen. In this one we also have the 2 electrode. These 2 electrode connected by a very fine wire of the tungsten or maybe any other substance, and we close this bomb and we place this bomb in the bomb calorimeter in this bigger container, and then we attach these 2 electrodes through a power supply and we increase the voltage. This coiled butter becomes the heat up, temperature increases, and whenever the temperature becomes equal to the ignition temperature of the fuel, at that time the fuel undergoes the combustion reaction suddenly. Why very fast and suddenly? Because it is surrounded by the excess amount of the oxygen and it undergoes the combustion reaction very fast, very suddenly, and whenever we have the uncontrollable combustion reaction, that is called the explosion. If we are burning the LPG gas under the control way in our kitchen, it is called the combustion. But whenever the gas present in the LPG undergoes the sudden combustion, it is called the explosion. So since this fuel undergoes the explosion suddenly, that's why it is called the bomb. So what we do? We increase the temperature. Whenever the temperature becomes equal to the ignition temperature, the fuel burning will start and this valve will break. And whenever this valve will break, the reading in the voltmeter again become the 0. And by knowing that one, whenever the reading of the voltmeter become the 0, now we know, okay, now combustion is started. We take the time, slowly the temperature of the water increases. By the reading of the thermometer, we can calculate what is the increase in the temperature. Suppose if fuel is the organic fuel, hydrocarbon, it may have the formula CXHY. It react with the X plus YY4O2 to give the XCO2 plus YY2 H2O. This is the common reaction. Suppose we have the ethane gas. Ethane gas required the 7/2 oxygen gas for the complete combustion to give the 2 CO2 gases plus 3 H2O liquid. All these experiment occurs at the room temperature, and at the room temperature water is taken as H2O is taken in the liquid state. Okay, I will again use this equation. Now the heat release is calculated as the Q m C delta T. Mass of the entire system including the fuel is always constant. Either you do the experiment today in the same instrument or you do the experiment in the next day in the same instrument, mass of the instrument always remains the same. Heat capacity, we are using the same material today we will use the same material tomorrow. So heat capacity also remains the constant. Then mass of the bomb calorimeter, heat of the bomb calorimeter constant, that is called the Z. Heat capacity of the bomb calorimeter, for every given bomb calorimeter it has a fixed value. Okay, and I told you what is the mass of fuel, always we have to take in 1 gram. Then if this Z value, heat capacity of the bomb calorimeter, is given to us, what we have to do, we have to just find out what is the increase in the temperature. Just calculate the Z delta T, you will get the energy released by the 1 gram of the fuel. Because we have taken the 1 gram, this is the energy at the constant volume. This is the energy at the constant volume. This energy provides the energy value which is released by the combustion of 1 gram of the fuel. If this heat given by the 1 gram multiplied by the molar mass, what we have? We have the change in the internal energy per mole. This heat at the constant volume, the whole process occurs under the constant volume. Q is the heat released by the 1 gram of the fuel. If Q is multiplied by the molar mass of the fuel, what you will have? You have the heat released as the constant volume by the combustion of 1 mole, and internal energy is also the heat released at the constant volume. So this Q into molar mass provide the heat release at the constant volume, that is the change in the internal energy. But we want to calculate the delta H. Delta H means enthalpy change during the reaction. Then what is the formula? Delta H is equal to delta U plus delta Ng RT. You have to find out the delta Ng. What is the delta Ng? Number of the gaseous product minus number of the gaseous reactant. Suppose in this reaction, how many gaseous product? 2. Minus how many gaseous reactant? 1 gaseous reactant here and 3.5 gaseous reactant here. So 2 minus bracket start 1 plus 3.5 means 4.5. 2 minus 4.5, that become the minus 2.5. So delta U, you know from the bomb calorimeter. Delta Ng, you know from the equation balancing, or you know, if it is given in the joule, write the value 8.314. If it is given in the calorie, write the value approximately 2. And temperature has to be mentioned in the question. If temperature is not given to us, you remember all these process occurs at the room temperature, that is the 298 Kelvin. Okay, so that's all from my side today. Thank you.